Don't know the answer? Ask the Naked Scientists.
Hello and welcome to this week's Ask the Naked Scientists with me, Sue Marchant, and Dave Ansell. What's new in the world of science for you?
Well, there's a quite nice story this week. The Japanese have launched a sailing ship, but it's not a normal sailing ship which drives around on the sea. It's out up in space.
Right.
This is a thing called Icaros, which sounds like interplanetary kite craft accelerated by the radiation of light. Basically, the problem is if you tend to have a space rocket, you can get lots of power, you can accelerate very, very quickly. But the problem is, if you want to go a very long way, you've got to carry your own fuel with you. And so the further you go, the more fuel you've got to carry. So the bigger the rocket you need to lift the fuel. So if you want to go a bit further, you need an even bigger rocket to carry all the fuel to get the first bit. And then you need even a bigger rocket to carry the second bit and third bit. So rockets get obscenely huge once you start going a long way across the solar system. So if you can somehow take your fuel with you or use some fuel which you can find out in space, and that's wonderful. And surprising as it sounds, actually you can sail on light. If light bounces off a mirror, it applies an incredibly tiny force, but the force is still actually there on the mirror. You can't fit it with yourself because it's far too small. It's like billionths of a weight of an apple, billionths of a Newton. But it is there, it's real. And the Japanese are sending up a little satellite that's actually on the way to Venus because it's piggybacking on another satellite which is going to study the weather on Venus. And it's flying off to Venus and it's going to send out this great big big mirror, so a big plastic sheet, 50 metres square. It's holding it out there because the satellite is spinning slowly and the centrifugal force is holding some weights at the end and holding this big sheet out taut. And it's the first time anyone's tried it, and with any luck they'll be able to very slowly get faster and faster and faster just by using the pressure of the light from the sun.
I think you'd like to go into space, wouldn't you?
It would be nice, although a little bit pricey at the moment.
Yeah. No, I mean, if they said, Dave, we want someone to go up there and, study Mars, you might never come back.
Actually, going to another planet would be absolutely incredible. I still find it incredible. I remember sort of at 12 or 13 actually just looking at the photos, I think it's from the Viking landers on Mars, just thinking, that's not this planet. That's not everything we know is a tiny part of one lump of rock. And the little landers on another lump of rock entirely millions and millions and millions of miles away.
Now, we've had an email in from Lisa who says, how far is the Earth to the Moon?
It varies from about 360,000 kilometres to about 405,000 kilometres. So the Moon goes around, its orbit is slightly elliptical, and one part of the month is a little bit closer than the other, which is why the Moon does change in size a little bit, but only by a few percent, but not an awful lot.
Let's go to the phones this time. We've got Tony on the line. Hello, Tony.
Hey, ma'am.
What's your question, Tony?
Well, perhaps Dr. Dave could explain exactly what an atom is.
I'm sure there have been textbooks written on the subject.
I'm sure.
OK, an atom was thought to be the smallest lump of matter which you could chop something up into at all. So if you have an element, so something like hydrogen or iron or copper, an atom is the smallest lump of stuff, the smallest lump of iron, which is still iron. If you chop it up any more, it stops being iron. So the structure of an atom, it's got in the centre, it's got a very, very small. It's absolutely tiny. It's sort of, I think, an analogy is about the size of an orange in the whole of St Paul's Cathedral dome. So there's a little nucleus which is very, very small, and that's where 99% of the mass of the atom is, and that's very, very positively charged. And then sort of flying around sort of in a slightly fuzzy kind of quantum mechanical kind of fuzzy way, there's a load of negatively charged electrons around the outside. They're a bit like waves and a bit like particles, so you can't really say that they're sort of orbiting, but they're kind of going round in circles, and they're in a kind of strange sort of wave kind of like way. It's kind of it does my head in, let alone anybody else's. And then these atoms can interact with one another, so you can get sort of little interactions between the electrons, which makes atoms stick together and form molecules. So an atom of oxygen can stick to two atoms of hydrogen to form water, a water molecule, and other more complicated things like that.
It seems to me that it's, if it's like a football, let's imagine an atom's a football. It hasn't got any outer case to it. and yet it makes solid.
So how can it be so solid?
Exactly.
Well, the thing is that we're made out of atoms too. So although an atom has got lots and lots of space in it, I don't know if you ever played with very, very strong magnets. You ever tried to push two north poles of magnets together? They won't go, even though they're not touching. So things don't have to be solid to stop something moving towards them. And so, because the electrons are negatively charged, and if you push two atoms together, the negatively charged electrons will normally push each other apart. So the reason why it feels solid is because the atoms in your hand can't move through the atoms in the table, because they push each other apart, they repel each other. And so even though it's all mostly space, you can't push an atom through a table, so it feels solid.
Tony, thank you so much.
Thank you. It's very clever, Vin. Bless you. Bye.
Bye-bye. Now then, let's move over to one here that's come in by email. And Rafiq says, when does a theory become a fact?
If you're a good scientist, the simple answer is never. If you're a scientist, there's always doubt. And what you think the world is doing might not be right. All we know is that, as far as we can tell, for example, if we have a theory that if I let go of this pencil, it's going to hit the floor.
Yep.
I don't know for certain that's going to happen. All I know is that the last 10 billion times I've dropped a pencil, or people have dropped pencils, they've fallen towards the floor.
Go on then, Dave.
I can do the experiment, and so now it's 10 billion and one times we've let go of the pencil.
It did, but it bounced.
And it bounced. So my theory that if you let go of a pencil, it hits the floor, no one has discredited it, but you're never 100% certain. You've always got to have that little element of doubt that it might be wrong, because otherwise we'd never come up with any new ideas. And we'd just be thinking that the world was flat, because that seemed like a good idea, and we never had any doubt in the idea that the world was flat. And this slightly confuses people, because in everyday life a theory just means something which isn't very certain, whereas in science a theory is as good as it gets. A hypothesis is someone who's just had an idea. You might have an idea that if I plant this stone in the ground, it's going to grow a green-orange tree. And that's a hypothesis. And until we test it, it can't be a theory. So if you test it and the evidence shows that your hypothesis supports your hypothesis, and you've got quite a lot of evidence and several people agree with you, then that turns into a theory. And it never gets any better than that. Some things are called laws, but that's purely historical. They're no different. They're actually theories from a scientific point of view. We can be very, very, very certain about things, but you can never be 100%. So there's lots of the basic theory of gravity. You know that in normal environments, when we're running around on the Earth, 99% every time everyone has tried, things have fallen downwards. But you never know. The theory might stop on next Tuesday. There might be something strange about gravity we don't know that will mean it will stop next Tuesday. We're really quite certain it won't. That doesn't mean that it couldn't do. And there's things like theory of evolution. Lots of people get slightly confused that it's just a theory, so it's not very certain. There's huge amounts of data backing it up. There's thousands and thousands of people's lives' work have been backing it up, and we're really quite certain that something which looks really quite like the evolution, that the world works really quite like the theory of evolution. But we can't say it's 100% true, because, to be honest, the universe might have been made 2 seconds ago by some kind of strange creator and made us think that I've been living for the last 30 years.
Now, Dr. Dave, Jill wants to know what causes a tornado.
Okay, a tornado, they tend to form in very, very warm places like the United States. Mm-hmm. You get a few here. Mm. They tend to form when you've got wind going in different directions on the ground and a few thousand feet up. So you got the wind blowing in one direction high up, another direction low down. And so if you imagine the air in between, where the junction between these two lumps of air, which are moving in different directions, is going to get rolled if you're rolling a pencil between your two hands. So that's rolling quite fast, and you get quite a lot of rotation there. Then if you get an area where you've got very, very rapidly, lots of hot air low down, it's been very, very sunny, it's lots of moisture, that's going to start lifting up. And somewhere else air is going to come down, and that air coming down can drag this spinning air down to the ground, at which point it can pick up more moisture, and then you get more air pulled into it. And as if the air is pulled into the centre as it's rotating, it spins faster and faster, a bit like if you ever played on a roundabout and you move into the centre, it spins faster and faster and faster. And so the air is spinning incredibly fast. You get quite a strong updraft up the middle, and it will lift things up and be incredibly lethal.
All right, well, let's go to the phones right now. We've got Mark on the line from Dunstable. Hello, Mark.
Hello, Sue.
What's your question?
Hello, Dr. Dave.
Hello.
The question I wanted to ask you was, I've heard there's a thing called a fuel-air bomb. It's supposed to be the second most powerful weapon apart from an atomic device. They call it a daisy cutter. But I just wondered what this thing is and...
Sounds dangerous.
yeah, it does.
Dave.
They are lethal things. I think the standard there was a bomb, especially during the Vietnam War, which Americans used mostly for clearing jungle, so as they could then drop people out of helicopters into it, which they called the Daisy Cutter. I think that was just a very, very large conventional bomb. So it was about a 7-ton bomb with very little casing, so a huge amount of explosive. So it would land on the ground and just blow trees down all the way around and create a flat area. Absolutely lethal way of doing it. So as the Viet Cong couldn't get close, so they could see the Viet Cong getting up close to where they were trying to land the helicopters, and the helicopters would have a chance of landing, which is a scary way of clearing trees. The fuel air bomb is a slightly more modern thing with an explosive, a normal conventional explosive, something like TNT. You've got both the fuel and the oxygen mixed into your explosive. So you have nitrate groups in the explosive, which have got oxygen. When they burn, they release the oxygen, which then reacts with all of the carbon and stuff inside the explosive. And then that it burns even more, so it expands a huge amount. But the weight of all this oxygen in the explosive means that an explosive has actually got far less energy in it than petrol has. So it's got a third or a quarter of the amount of energy of the equivalent amount of petrol.
Yeah.
So there's a limit to how big a bang you can get from a certain size bomb. So the Americans, being cunning, and various other people did something similar, instead of using oxygen being carried with the explosive, you can make a bigger bang by using oxygen in the air. So you get things called fuel air bombs, which just carry a whole lot of petrol essentially in them. They squirt that petrol out into the air, and then they set off a small bomb. All that petrol just is nicely mixed in with the air. It reacts incredibly quickly, and you essentially get a bomb which is 4 or 5 times bigger than it would be otherwise. And it also has nasty effects of sucking lots of oxygen out of the area below you because you burn all the oxygen, so people can suffocate in it as well.
Oh, awful.
Horrible.
It's nice to have you on. Thanks.
And Dave. Bye-bye.
Thanks for listening. Bye-bye. If you're enjoying Ask the Naked Scientist, then you might like to check out The Naked Scientist, our regular roundup of the world's best science. Each week we take a look at the latest science news, talk to top researchers working at the coalface of discovery, and also get our hands dirty with a science experiment that you can join in with too. So make it a date and prepare to strip down science on the web at nakedscientist.com/podcast. All right, let's go to our next question. This is from Paul near Stevenage. He says, is it possible that the oil from the vast US oil spill could be roped off at sea, then sucked up and be reprocessed? After all, water and oil don't mix, so it's already separated. If it can't be used as fuel, could it not be used for light industrial use, etc.?
The simple answer is yes, if you can get hold of it. You certainly can do that sort of thing. In fact, quite a lot of oil wells, the way they push more, get the last bit of oil out of an oil well, is by pumping seawater down and squirting that under the oil. That pushes the oil up. And so sometimes when you're getting near the end of an oil well, you'll get a mixture of oil and water coming out. And then they have ways of separating it, and you can get the oil off and separate it out into its all these useful components and turn it into fuel and lubricating oil, whatever else you want to do with it. So yes, you can certainly do that. The problem is that the slick is spread over thousands of square miles now, and it's not so. And it's also, I think, quite a lot of it isn't the sort of slick which you imagine in your head of a sort of big, thick layer of oil on the surface. Quite a lot of it's just lots of little globules of oil floating in the water, in the top sort of metre or so of water.
Yeah.
And so you'd have to process billions and billions of tons of water to get the oil out. And I think they are attempting to skim the oil off near where the oil's escaping, where it's quite concentrated. And we're talking about having skimming ships, which sort of drive around and do exactly what you're saying. They're sort of little tankers with booms, and they kind of suck the surface layer of water and oil in, and they try and separate it, and then they go and process it later. But once it gets spread out, it's very, very hard to collect because it's just over such a huge area.
Now, let's go to our next question, and this is from Luke. Luke says, when I make jelly, if I leave it in the fridge for a while, it often forms a layer of ice on the surface. My fridge isn't freezing, so how come I get this ice on my jelly? It's very annoying.
I guess there are various things it could be. One thing which has sprung to mind is that things can get cold in the air temperature around them, which is the reason why you get frost on the ground, even though the air above it is above freezing. Basically because if something is warm, it will radiate heat, lose heat as a form of light called infrared light, which is what the thermal imaging cameras you sometimes see on police TV programmes are doing. They're looking at this thermal infrared light coming off, and things can lose quite a lot of heat like this. And therefore, if your jelly is sitting right underneath the very, very cold cooling bit at the top of the fridge, then the cold bit at the top of the fridge will probably be radiating less heat than your jelly is, so it will cool down. And if your fridge is right on the edge of things freezing, then it's possible that's enough to just push it over the edge and make it freeze. The only other effect you might get is that evaporation can cool things down even near zero when it's freezing, when things are freezing, and it's freezing temperature, and that might be cooling it down a little more. The other thing is you might be just putting the jelly in a different bit of the fridge to everything else, which is just a little bit colder and will just freeze.
Now, let's go to Jenny in Northampton. She says, how come our ears are designed to filter out radio waves while we were evolving, yet we hadn't discovered how to transmit them? Dave?
The first thing is radio waves and sound waves are actually very, very different. A sound wave is a vibration through the air, and our ears can pick up vibrations which are from about 30 times every second, up to, depending on how young you are. With me, it's stopping about 16,000 times every second vibrations, or if you're young, 20 or 21 times, 1,000 times every second. As you get older, the higher frequencies, the higher pitches, you lose them very slowly until eventually you find it hard to understand what people are saying in sort of very busy situations and things. Whereas radio waves, they're not a vibration in the air, they're a vibration in the electric field, so they're an electrical phenomenon. They're actually much more related to light than they are to sound. And they're basically like a very, very light is a wave, it's called an electromagnetic wave, and that's vibrating about 1 with 14 zeros after it every second, whereas radio waves are vibrating about 100 million times every second. It depends on exactly where you are on the dial, but that sort of order. So it's not really the question as to why your ears can filter out radio waves, it's why your eyes can. And really the question, the reason why we don't collect radio waves is they weren't very useful. It's taken billions of years of evolution to develop high-tech ears and eyes. And if there wasn't really there weren't very many radio waves around, they weren't particularly useful to find anything which will make us survive. We just haven't evolved to be able to pick them up. We can only actually detect a very, very small part of the light spectrum, let alone so we can't see things like ultraviolet, which bees can, which means that they can see flowers. We can't see infrared, which some snakes can, which is really useful because it means you can find things which are otherwise really well camouflaged, because all, especially warm-bodied animals, are glow in the infrared really brightly. So it's basically there's been no reason to evolve it, so we haven't.
Dom wants to know, what is a liminal or a limaloo and a liminine?
I can make a guess.
Oh dear.
The problem with these chemical terms is that you tend to, that very, very tiny changes in the spelling can completely change what the chemical is. So I'm guessing at roughly what you're meaning, because there's a whole range of different things which it could be. Limonene is a really common thing. It's if you ever got an orange and you've got the zest of the orange or the zest of a lemon, that kind of really smelly oil which comes out of the skin. It's called a terpene. It's a hydrocarbon, a bit like petrol. Actually, if you get an orange skin, I did this for Kitchen Science a while ago, and you know, if you kind of squeeze an orange skin, you get this spray of this really smelly compound coming out, this smelly liquid. If you do that into a candle, it'll catch fire, and you create these little fireballs.
Right.
So if you get a really, really juicy orange skin and then you squeeze it onto a candle, you can form these little fireballs.
Be careful, please.
Be careful, don't set fire to your house.
No.
But it's lovely when it works. And so that's a really flammable thing. I think it's actually the orange makes it in order to discourage insects, because it's quite a good way of, insects don't like it, it's quite insecticidal. And you can sometimes use it to, in fact, some mosquito repellents use it.
Oh, yeah,
They smell very
like a
strongly,
citronella. Yeah.
it's the same smell, it's all the same compound. There's a couple of other things in there as well, but that's the main one. I think there's various other compounds. There's things like limonene, which is found inside, which is just another random compound, which is to do with lemons, which is found inside orange and lemon seeds. I think limonal is something which there are limonals which chemists can make from limonene. So there's all sorts of different compounds, some of them related, some of them not, which people first found in lemons, so they call them lemon something or other.
Let's go to the phones. Let's say very good evening to Morgan. Hi, Morgan.
Hello, Dr. Dave.
Hello.
I would like to know why I get an electric shock every time I get out of my car.
It's actually quite related to, if you ever got a balloon and rubbed it on your hair, it's slowly, in fact, electrons are slowly moving from your hair onto the balloon, and the balloon slowly charges up. Or if you've taken off a nylon jumper, every time the nylon touches a bit of your hair, a few electrons jump onto the nylon, and the nylon becomes more and more negatively charged, till eventually that builds up enough charge that the electrons want to flow back to you. They flow through the air as a spark, and it makes that crackling noise, and it's quite painful. If your car moves through the air, something similar can happen. I'm not quite sure which direction the electrons are moving, but one way or the other, and slowly your car will charge up. Now, most modern cars have reasonably conducting tyres, so that charge will get get lost to the ground, and so you won't be too charged up compared to the ground. You won't get out. You won't get too bad a shock. It's a really major problem with helicopters. But if you've ever seen a film of a helicopter dropping a diver onto a ship or something, the guys on the ship actually have to get a sort of metal hook and hook the cable below him before he gets off, because a helicopter can get so charged up that I think some people actually can get electrocuted when they touch the ship, because all the charge on the helicopter, which is huge because the rotor is going through a huge amount of air, can build up enough that the guy can get electrocuted if it passed through him. So I would have thought it's that your tyres aren't quite as conductive as they should be.
It's quite an old car.
It could be oldish tyres. Sometimes people have those little straps at the back of the car.
And yes, I remember those, yeah.
Yeah, the idea is, especially when tyres were made weren't as conductive as they are normally now, the idea of those straps was when you stopped, the strap would fall down to the ground and all the current would flow through the strap and not through you.
Thank you very much.
Take care. Bye-bye.
Bye.
Let's go to the next phone now. We've got John on the line from Essex. Hello, John.
Hello, good evening. Dr. Dave, my question is about gravity. I think we can insulate, can't we, against all forms of energy like heat, light and sound, but why can't we insulate against gravity? Because in order to get a vehicle to leave the Earth, we're surely going to have to insulate against gravity.
Gravity itself isn't really a form of energy. You can get gravitational potential energy, so if you lift up a book and that's gained energy against gravity and you let go, it falls down. But the force of gravity is a force. Now, we can effectively insulate against electric fields and magnetic fields, but that's because with an electric field you can get positive charges and negative charges. Therefore, an atom might have a very, very strongly positive nucleus, what we were talking about earlier. But if you have the same amount of charge but negative charge around it, overall there's no electric charge, so that atom is neutral.
But how are we going to overcome it? Because you were talking earlier in the programme about the problem of lifting tremendous weights of fuel to get these vehicles off the Earth. How are we going to do that?
I mean, as far as we know, there's no way of doing it, and so you just have to put a huge amount of energy in to lift something against gravity. Part of the problem with getting off the Earth at the moment is that you've got to lift the fuel, to lift the fuel, to lift the fuel, to lift the guy at the top. And so if we can get other ways of doing it, like there's things called the space elevator, where the idea is you basically run a string from a satellite out beyond geostationary orbit all the way down to Earth, and then you can just build a machine to climb up the string. And that would work if we could get a string which is strong enough, which is beyond
long
technology
enough.
at the moment. The length isn't the problem. The problem is if you made it out of steel, the top would be far wider than the Earth is because it wouldn't be able to support the bottom.
I was rather hoping you could have a pad of insulating material where everything above it would be weightless, and then would solve that problem.
Yes, that is a thing which many science fiction writers have hypothesized, but there is no evidence that it exists. It would be really nice if it did, because it would make lots of people's lives a lot easier.
Yeah.
But,
Okay, well, you've answered my question. Thank you very much indeed.
Thank you very much, John. Bye-bye. That's it for this week. Our doctors will be back with me next week for more Ask the Naked Scientist. But don't forget, you can also catch them on the Naked Scientist podcast, which you can find on the Naked Scientist website, www.nakedscientist.com.
The Naked Scientists are sponsored by the Wellcome Trust, the EPSRC and UK Fast. For more information, look us up online at nakedscientists.com.